everybody. Good afternoon. Hope you guys are coming from a post-lunch stupor, and I'll try to make it interesting and hopefully enjoyable here. So thank you again for inviting me. It's great to be here, and it's great to be live. I've been doing a lot of Zoom things for the last year and a half. I can't tell you how tired I am seeing myself talk, hear myself talk, and seeing people is really exciting. So what I want to talk about today is a lot of different things. I'm going to try to cover a lot of topics in a very small amount of time, and hopefully I'll do it justice. I want to talk briefly about the metaverse, because why? Everyone's talking about metaverse, right? It's in the air now. Facebook changing name to Meta, for example. So we're talking about metaverse and why it matters, and why it matters to all of us here in the census community. Then I'll dive a little deeper into AR, and more specifically into laser beam scanning for near-eye displays, which is really what I want to get into the meat of. Since it's a sensor and actuator conference, so I figure I should talk about sensors and actuators. Okay, so without much further ado, what is metaverse? I have no idea what this is. Word's been used quite a bit. Everyone's talking about it. It's all excited about it. What is it? I'm not sure. There's a definition. Meta, of course, beyond universe. Okay, interesting. What is interesting, however, is the fact that whether you like it or not, and I'm not so sure if I like it, I shouldn't say that, but okay. We are going to a world of augmented reality. We are going to a world where we'll blend physical and digital worlds seamlessly. That's happening, whether you like it or not. Hopefully, it'll be for the better. That's happening. And if you accept that thesis and you accept that day is going to come, then the definition that Matthew Bell, who's a famous VC, gave is a really good one about what the metaverse is, the AR is. And that is really having a very massively scaled interoperable network, real-time virtual worlds. They're synchronous, persistent, you have presence and interaction and continuity, right? So very, very important words because they mean something technically, it means something tangible in terms of how you develop these things. So when you want to blend seamlessly a physical world and a digital world, if you will, like I don't know why if you showed the HoloLens yesterday or not, I think you had a demo here, hopefully you did. But when you put on a HoloLens type of a device and you blend the digital and the physical worlds, the complexity of what it takes to do that is really extraordinary. And you take that a little further and you juxtapose the entire framework of life, of social interaction, of sports, of entertainment, of journeying, all those things you do in the physical world, to do it in a virtual world and do it simultaneously is what the metaverse is supposed to be. Okay? And I think it really encapsulates this definition and what that is. So when I think about the structural framework for the metaverse, I really think about people's places, objects, and spaces. That is sort of the universe, if you will, right? And that's what occupies this metaverse. Like you do in the real world, so you should also do in this virtual world. And in order to live and coexist there, then certainly you have to have the ability to interact, you got to perceive, you got to be able to sense, and you got to persist, always be there. Those core modalities are really important in order to allow people's places, spaces, and objects to interact together. Okay, so you have to have that. If you accept that, then underlying that, you have to have core technologies. You got to be able to sense, you've got to actuate, you're going to have to compute, and you're going to have to connect. Those have to come together in order to allow this framework to occur. And that's what it comes down to in terms of how we think about technologies that can support this type of framework. So from a gateway point of view, how do you get into the metaverse? And so what I wanted to then focus on is, okay, there's a lot to cover here. We can't possibly do justice to everything. And this is a whole day conference, quite frankly, to cover everything. But if you look at the gateway, how's your on-ramp? How do I get into this metaverse? How do I start to engage in this metaverse? There are many ways. The simplest way is, of course, today, you can do it. You can do it with your smartphones, your laptops, your gaming devices, other IoT devices, so you can get into the metaverse. If you want a little bit more immersion, then you have augmented reality, and you have wearable devices. You have embedded devices, and for full immersion, at least today, you've got the VR headset, you get total immersion, and then in the future, we'll have more devices coming up. Okay? And what I want to focus in on really, and the topic of this discussion today is really about AR. Today, the experience for AR is typically through a handheld device, a laptop, PC, tablets. AR is starting to get more traction. There's a lot of use, particularly industrial segment, enterprise segment. Certainly, Microsoft has done a lot of work with both the military as well as scientific and other type of applications. But AR glasses is probably the next thing that's going to allow us to experience AR in a really tangible way and a very immersive way. So I want to take a little brief pause here. When you talk about the modalities of interaction in this new world, this metaverse world, talk about the ability to perceive, to experience, to persist. You have to have foundational basis. You have to have foundational technologies to enable that. There's a whole range I'm not going to go to cover today. There's certainly visualization, but I mean optics, photonics, optoelectronics, and so on and so forth. There's the compute side, there's the connectivity side, but really for the purpose of this conference, the purpose of my talk today, it's really about the sensing and actuation side. Whole range of sensors have to come to bear here, including visual and olfactory. I'll be able to smell the vision, if you will, right? It's coming. You may laugh and think it's funny, but it's true. It's going to come. Haptics, for sure. Embedded sensors, biosensors, maybe even dust, perhaps. I'm not sure. I've heard of dust today, right? Some kind of dust thing. All those things need to come to fruition. They're already there today, and they have to be further enhanced, and new sensors have to come out. But again, I come back to say, okay, the way to really experience it today is through seeing it and through AR and through imaging. So that's the really purpose of my talk today. We'll focus on that. And one final thing, and a key requirement, as you develop and design systems throughout, in any aspect of this, you have to have low power, you have to have low latency, you have to have high efficiency, you have to have high quality of service, and security. So all these things have to be built into every piece, every framework of this new overlying structure. Okay, let's get into it. So, again, AR wearables, AR glasses. What are the challenges? What are the opportunities? You sort of have two camps today. On the right, my right today. On the right, you've got the informatic displays, the smart glasses. Practical, useful. On the left, you have immersive and niche. Niche doesn't mean a bad thing. It just means that it's a very specific application. It's much more immersive. It's much more intensive. But you have those two worlds. Okay? And what divides them is basically, on this part, we want to really concentrate on having a device that you can wear all day long, that's fashionable, that's lightweight, it's unobtrusive, that can work inside and outside. We want to add to that even more capability. And what's difficult is it's hard to get all of that into a form factor this small, right? Trying to cram in what's in the HoloLens as an example into pair of glasses is very, very difficult. Now, laser image scanning is the core technology we're going to talk about today. That's a core display technology that we believe, it does certainly support both markets. Both devices actually can and do use laser image scanning. What I want to leave you with is that as you think about devices, it goes beyond the display. So trying to do this kind of a platform is more than just a display, as I'll talk about a little bit later. But nevertheless, as an actuation point of view, I'll talk about laser image scanning and how that can support these markets irrespective of the end application. The other thing to think about is about form factor, performance, and functionality. So we want to get to a device that you can wear like a pair of glasses all day long, and you want to have everything. Today, wherever you are, if you look at this chart, is that if you sort of plot this device size, if we will, so HMD, head-mounted display, is very large, helmet-like device, down to a pair of eyeglasses. And then the other axis, if you look at the immersivity, going from sort of simple head-up display, infrared display, into a totally immersive, interactive display, there's a big gulf, there's a big chasm today. So today, we are here. We have glasses that are informatic, then we have bigger devices that are somewhat immersive, but what we want to try to get to is up and to the right. We want to have glasses that can be completely immersive and do everything you can with a very sophisticated device in a very small form factor. Okay, so to go from the HMD to a wearable device, a pair of glasses, many things have to come to bear. I'll focus on the display part today, given the amount of time that we have. And so the first order, there are two things that will determine that. One is to have a very near-to-eye display, a very small, compact display. And along with that, a very efficient combining technology, ability to take the light from the light engine and bring it to your eye. That's what's really important and useful to have to enable this journey to begin. I'll also say that we're too early on for have mass adoption of such a device for the consumer market. We believe, a lot of us believe, that the application, the use case is really for informatic display, for enterprise and industrial and non-consumer uses. So what we say is, look, start with a good device, start with a good display, start with something you can wear all day long, Start with an application where you can use it, where you have informatics that helps workflow improvement, for example, remote maintenance, factory operations, any enterprise application. And over time, as technologies mature, you can add on more and more sophisticated processing, sophisticated rendering, sophisticated displays. And so laser beam scanning is, we believe, of course selfishly, the de facto technology that can enable the AR market and give you those attributes. And the goal here is to have all-day wearable pair of glasses, lightweight, bright, and have the right level of performance. I won't go into all the details over here, but basically what it means is that you need to be able to wear this inside and outside. You got to look fairly fashionable. It has to have very low power, very lightweight. It has to have decent performance. By decent, I'm talking about, depending on what you're trying to do, if you're just doing simple informatic displays, you don't have to have a very broad field of view, nor do you have to have very high resolution. If you go into a very immersive application, then of course you have to have a bigger field of view and also have a bigger resolution. But there's some characteristics that you want to enable. And again, laser beam scanning supports both, but this is the kind of things and kind of metrics you need to think about when you design such systems. So I've talked about LBS. Some of you know what this is, some of you don't know. How does it work? What is laser beam scanning and how does it work? Very simple. In this sort of diagram here, you're starting from your left to your right. You see an example of a MEMS die. This happens to be an electromagnetically actuated mirror, but there are different modalities of actuation I'll talk about in a second. But the die is very small, as you can see, in terms of the image over here. Then die goes into a package, and the package itself is also quite small in this illustration here. But the way it works is very simple. You've got one or two mirrors, depending on whether you have a biaxial or two monoaxials, but you have a mirror. You have three lasers that are pre-modulated with the data. They go through some calming lenses, go through some beam combiners. This combined beam, it's a mirror scans back and forth in a raster scan. Or in the case of Augmented, it can do a Lisa-Ju pattern, but nevertheless, it'll scan back and forth, and the image will be displayed on the screen or to your eye. The photograph here is actual rendering, the actual pair of glasses that we have a demo. I didn't bring here today, but I'll be happy to, if you want to see such a demo, send me a shout out, send me an email, and we can figure out how to get it to you. Nonetheless, we have over here the photonic module, electronics module, that it's embedded in a temple of glasses, and then that's how you get the image to your eye. So here's a quick little animation of how this thing works. So basically, you've got two monoaxial mirrors over here. You have red, green, and blue lasers that are emitted, that are coupled through dichroic beam combiners, hits the mirror, mirror scans back and forth in two axes, and gives us an image that can go onto a wall or onto your eye through some kind of combining optic. Here's what it looks like. So this is an actual photograph taken through the glasses of this device that's rendering information in your field of view, basically. So you can well imagine using this for fixing tools, repairing tools, logistics in the factory, so on and so forth. So what are the underlying technologies? So from an ST point of view, we developed what's called a MEMS ScanR family of products. And these are basically composed of micromirror driver, as well as a laser diode driver, all designed to support all the needs of augmented reality: low power, high performance, lightweight, so on and so forth. So in this case, we have two monoaxial mirrors. There are many architectures. We like to have two mirrors. We think it's a much better architecture in terms of flexibility of design for an optical light engine. But there's also biaxial mirrors as well. But we have two mirrors, mirror driver, and a laser diode driver. And really the first of family is what we call a Star One. Star One is our first foray into this. It's basically, it's a thin film PCT mirror. So we're shifting from electrostatic magnetic into a piezo-based system for actuation. It's a 720p mirror. It's got a pretty big field of view, 65 degrees optical field of view, and has a range of brightness depending upon your end application and the losses of the optics. So if you have a lossy optical system, you have higher brightness. If you have a very efficient optical system, lower brightness. And this is an example of what the board looks like. Over here at the end is the optical light engine, so photonics module, and then the electronics module is over here on the PCB. And you can see in the diagram over here how it works. You basically have your electronics, your mirror drivers, laser diode drivers, the control logic, all that embedded on the PCB. And then on the photonics module, you've got your lasers, your photodiodes, your combining optics, and your mirrors, essentially. That's how it really works. Okay, so what's good about laser beam scanning, what's interesting about laser beam scanning as opposed to other type of techniques for other devices, technologies for near-eye display, is that it allows you to have a holistic design and design a system that you can optimize around certain variables. In sort of example diagram where we can talk about when you design a system, you have to think about many factors: size, weight, power, brightness, field of view, and so on. All these things interact, obviously. You're not going to get all of it. You can't optimize everything. Right? You got to choose what you want to design around. And what's good about laser beam scanning is that there's some flexibility and design choices that you can make that can deliver a range of performance around an envelope. And the reason why is several-fold. One of the key things about it is that we went from electrostatic actuation to piezo because we were able to get a much more efficient actuation, much lower voltage, and much lower power. In fact, we were able to cut the power down by a factor of 10, at least on the resonant mirrors as we go from electrostatic to piezo. And this is where the trade-off comes into play. If you want a big field of view, you can increase the voltage. You'll have a little more power, but you can do that within your envelope of design. If you want the same field of view, but you want a higher resolution, you can change the frequency, for example. And you can play with those dynamics in the system. And so depending upon how you want to design a system in terms of size, weight, power, resolution, and so on and so on and so forth, there's optimization you can do around it, but the system has to be designed as a system in general. In other words, you have to think of what you want to do and then back into it and design it. And so having laser beam scanning kind of a platform allows you to do that in a very cogent way. And so as we think about the future, as you think about efficiencies, as you think about actuation efficiencies particularly, we want to get to lower and lower actuation powers or voltages. We want to get to much higher performances, and we do that through both materials engineering as well as a process development. And so what I've shown here is a roadmap. So today we're here, today's now, and we have a certain performance. What we're working on now is to continually improve the actuation force by, for example, going from say, PZT type material, solid gel kind of material to a solid state material to doped materials. So without going into much detail, we have a roadmap that can allow us to get greater and greater performance as you go to advanced materials, advanced actuation. And with that, we can then make even more greater trade-offs of performance. Either you can have the benefits of today's performance at a lower power, or you can have much higher performance at a little more power than before, but it allows you, the designer, to design products to take advantage of different attributes. But at the end of the day, the roadmap that we have put together is going to get us better and better actuation force, higher actuation densities, whether it's architecturally, whether it's materials. And we facilitate that in ST. We have a partnership with ULVAC, IME in Singapore, and ST, created what's called a lab and a fab. And the idea there is to do collaboration with some key partners in an ST production facility on future piezo materials and future piezo products. An advantage of doing that is that now we can go very quickly from R&D into production and have a very smooth technology transfer process that allows us to then very quickly go to market. Okay. And so this is a very interesting, and you can look up on YouTube and learn more about it, but it's been a great collaboration that allows us to do advanced piezo materials development. Okay, so shifting back to the glasses now. So more than just the laser beam scanned display device, there's a lot of technology that have to come into place to have functional glasses. You have to have lots of sensors, both MEMS-based and non-CMOS-based sensors, image sensors, motion sensors, temperature sensors, ambient light sensors, so on and so forth. There's a lot of technology. It's jam-packed into such a device in order to make it fully functional. On top of that, you don't see is algorithms like SLAM, which stands for simultaneous localization and mapping, for example, communications. Lots of things have to come together. And so to do that, requires quite a bit of integration technologies and partnerships. And so when we think about it, we have to, just on the display side alone, we need to bring together a lot of technologies and a lot of different players. ST certainly has a lot of these, but we don't have everything. So we always make sure that what we cannot do, we must then partner and build an ecosystem around that and a framework around that. So from an industry point of view, from a customer-facing point of view from the industry, we have a solution that the customer can draw upon. And so it's a lot of stuff that have to come together seamlessly. And the way we've done that is through creating alliance. So about a year ago, what is now? This is April, yeah. A year ago, we at Photonics West last year, virtual, we announced this so-called Laser Alliance, essentially laser scanning for augmented reality. There are 6 founding members, as shown over here, and since that time, we've grown it to over 22 companies. And the goal of the alliance is to build together the infrastructure, the framework, and the ecosystem of partner companies to have available solutions, technologies, products, and devices that ODMs and OEMs can draw upon to build their products. And so this is a nonprofit alliance. This is a group of people, companies coming together to make sure that today we're not standardizing. We want to make sure the supply chain is ready and things can work together so we can accelerate the growth of the AR market and try to support the industry. So this is an open alliance. It's a growing alliance. And as you can see, it has a range of different companies here that have joined and that continue to join as well. But the point here is that, in a lot of emerging fields, always think about ecosystems, how you bring partners together. There are competitors of ST here, or competitors of other companies. It's not a competitive thing. It's a very, very cooperative thing. It's a whole notion of rising tide lifts all boats. We really want to make sure the industry takes off. So I always invite people to think about, in the emerging markets, to create alliances like this to help product manufacturers and developers go to market quickly. So some closing thoughts. I know time is tight, and there's a tour coming, so hopefully I'm on time, Mahesh. I'm not sure. I think I am. So some observations. What do you conclude from this? I've covered quite a bit of material here. Hopefully it made sense. But what can you conclude from all this? Well, whatever the metaverse is, doesn't matter. I actually don't care what it is. Because at the end of the day, what we do know is that you have to have core technologies that will enable it to occur. That technology will be able to collaborate, be persistent, to interact, to move and navigate within there, all requires core technology. So no matter what the vision is, you have to have those core elements. Sense, compute, actuate, and communicate, right? Or connect. You got to have those, for sure. A lot of the pieces are there today, and mostly in very low levels of integration. HoloLens is an example of not that. HoloLens has done a really good job in terms of putting everything together but in a larger device. Many pieces exist today, but the biggest challenge, the first challenge, is a display challenge. Getting a small, efficient, lightweight, performance-driven display is really tricky and really hard, and that's why we spend a lot of energy and time within ST and our partners to build this laser beam scanned platform and environment ecosystem, if you will, to really help adjust that. But I'd be lying if I told you that's the only problem, that's the only challenge. That's the first challenge, the most important challenge. But really, the bigger question we're trying to answer is that, well, so what? It's a so what question. What do I do with this device? How do I use it? What do I do with AR all day long as a consumer? It's not clear yet. So answering those questions and answering what kind of applications are will really help to drive the market and also devices that go in there to support this market. And it's a great quote that Yogi Berra, who's an American baseball player and philosopher, some of you may know who he is. Great quote. Future ain't what it used to be. Got to really think about that for a second, right? It's a wonderful quote. It's always true. And he has such great, and then look him up. He has a lot of great quotes. No one knew 25, 30 years ago what the internet would become. No one envisioned Twitter or Instagram or all the other stuff we're doing today, right? No one had any idea. And so it shall be for the metaverse as well, okay? But no matter what it is, this is my point. No matter what it is, doesn't matter. At the end, you will have to have sensors and actuators and edge devices because you have to get in and get out of that space. And that is the message to everybody here, developing sensors, developing actuators. I'll give you an example of one actuator here in terms of the mirror, but there's lots of other things that need to come together. So with that, I hope you find it interesting. I hope I'm on time. I hope I didn't take too long, Mahesh. And yes. I am open to taking any questions.
So we have time for a couple of questions.
Thank you. Or comments even. Okay.
Bharath, Shiva from Applied Materials. One question. Where you showed the roadmap for your efficiencies, right? Is that tied to the field of view in any way on what needs to be achieved for an AR glasses?
Yeah, it is. It's a good question. So the question is the roadmap that I showed earlier for the piezo actuation force roadmap. The question is, does that tie into field of view? The answer is yes. So here's the thing: to get a higher field of view, it requires a lot of things. But to first order, you need to you need to take the mirror and open it more and more. Okay, all things aside, you need to have greater force and greater force density. And so going to a piezo material and doing that in a very efficient, low-power way, certainly having a much higher D33 or your piezo coefficient will certainly help along that line. So the answer is yes. It is intended for many things. It's intended for high fields of view, for really what's called MR. I wouldn't call it AR anymore, right? When you want to go to an immersive, holographic kind of rendering and world-locked content, you absolutely have to have much higher field of view, and it addresses that, or high resolution, or lower power. So the answer is, yeah, it's to give you those knobs to turn so that you can then have different attributes of your end device. But absolutely, it's intended to give you greater field of view and or higher resolution. Okay? Anybody else?
I see. I don't think. Oh, yeah.
Yeah.
Okay. Cyril from Bosch. More from a business standpoint, knowing that actually this metaverse thing is a very concentrated market, and also that the companies involved in that are pretty verticalized or trying to verticalize even more the technology offering for that. What is actually the, let's say, the go-to-market strategy of such an alliance? To be able to actually sell the technology to such companies that actually don't want anything to do with, let's say, external suppliers?
Good question. So the question is, why the alliance? What's the business model? So there are a couple of things. Alliance is just non-profit entity. Doesn't sell things, right? The goal is not to sell anything. By the way, Bosch, you should join. You're welcome to join. By the way, we'd love to have you. Honestly speaking, just putting it out there. On the record. Okay, putting that aside for a second. The alliance is intended to actually. Let me step back. There are the big guys we all know and love dearly. Fine. Okay, I love them too. Thank you so much. And then those actually sell product and make product, right? And they're two different camps. And they both coexist. And the verticalized companies, I won't name them by name, but they have their own business model. They are trying to do something very, very, very clear. But there's a whole bunch of other companies out there in the world who sell product, actually make product, who need to deliver physical products into a store, right, for example. And that's the market we address, because those are the ones who aren't verticalized. It's a large, I don't want to keep company names here, but they're all in Asia. You know who they are, okay? And some in the US, IT kind of companies, I'll say it like that. And they're not verticalized. They need product. They have applications. They have a customer base, right? Especially the enterprise space and industrial space. So the idea of the alliance is to make sure that we have, like about interoperable technology. So for example, laser beam scanner, you're using a Bosch scanner, for example, would be great. We'd love you guys for that too. Can couple into a diffractor waveguide, and what do you got to make sure the waveguide design looks like in order to make sure that you have efficiency of coupling, for example. Or I need to have a certain kind of optical element, right? That needs to be beforehand, for example. So there's a whole range of technologies that we want to enable so that every company who's not the big ones talking about don't have to do it themselves. We want to make sure, look, you go to market, we have these partnerships, the solutions exist, here's how it works, and that's the idea, right? So we're not going to go to market with a product, but we want to enable the market, enable the product, enable our end customers through making sure that these parts work together. Lasers and laser wavelengths, right? For example, right? And the spectral band with the laser, for example. There's a whole host of things that that come to mind, and that's the idea of the alliance: is to really reduce the frictional barrier for entry for these non-vertically integrated companies. Okay. Any other comments or questions? If you have time.
If there are no, okay, there's one more here.
Okay. Sure.
I was wondering, what is the limitation for the resolution, and is there physical limitation?
Well, at the end is the eye, right? so sorry, I mean, I think eye, if I remember correctly, you guys can, I think it's 60 pixels per degree, I think it's a limitation. I can't remember what it was. There's a limitation that'll come to my mind. So resolution is a very interesting thing. So the limitation comes from several aspects of it here. There is certainly the resolution of the device itself, the display device itself, right? Whether you're using a laser beam scan device or a fixed pixel technology, there's a resolution, right? You buy resolution, 1080p, whatever it is, right? 1440, 4K, 2K. So there's certainly resolution at the sort of fundamental device level, okay? Including laser beam scanning has resolutions there. A resolution limit there, not a limit, but really, the higher the resolution, the larger the chip tends to be for a fixed pixel. Higher the resolution, more power you'll consume on a scan system, for example. So there are always limitations to that. So one aspect is the actual display device itself. Has an inherent intrinsic resolution there. But then you have loss of resolution when you go through optical elements, so-called MTF degradation, modulation, transfer function degradation. That's what the eye perceives to see. So as you go through different optical elements, particularly as you go through diffractive type of materials on other optical systems, you then degrade the quality of optics, like a lens in your camera, for example. So, and then there's, of course, the human eye at the very end as well, right, and how well you see. So there's no answer to your question. The sum total MTF from the imager to your eye and everything in between is what determines resolution at the end of the day. So it's not an answer, but that's how the system works, right? So, but at the end, it's your eye. Your eyes, assuming you have a healthy eye, beyond, I think, beyond 60 pixels per degree, in that range, say, right? Your eye can't tell anymore anyway. And typically today, we're on the order of 35 to 40 pixels per degree is where we are. So we're getting closer and closer to the eye, okay? And I'll say one other thing parenthetically, you asked. The other thing we're looking at, we're developing some partners, had in the past, and the company out of Israel, which no longer exists, is what's called direct retinal scan. So another way of trying to image to your eye is to avoid the optics completely, by and large, and take the beam right to your eye and draw it in the back of your retina, essentially, called direct retinal scan. That's probably the ultimate way of probably getting the signal to your eye in the purest way possible. So. Sorry for a long answer for your simple question.
Very interesting. Let's thank the speaker.
Thank you,
Bharath.
Appreciate it. Thank you.